Hello everybody. We are going to start now the polymers, which is the 3A unit under your syllabus. And myself is Dr. Arudima Naik, Head of Department of Chemistry, Graphic Era, deemed to be University. Now the syllabus under polymers is first is we will be learning about the definition, the certain terminologies like the degree of polymerization, the functionality. Then we'll be coming and learning about the classification of polymers with certain examples, the types of polymerization like addition and condensation polymerization, the mechanism of addition polymerization. Under plastics, we'll be learning about the definition and characteristics, the thermoplastics and thermosets plastics, preparation, properties and application of PVC and bakelite. Under fibers, we'll be learning about the characteristics, the preparation, properties and application, especially of nylon and dacron. Under conducting polymers, we'll be learning about their characteristics, the classification with examples, the mechanism of conduction and the application of conducting polymers. Under biodegradable polymers, we'll be learning about its concept and advantages as compared to the synthetic polymers, preparation of polylactic acid and polyvinyl alcohol and their various applications. Now, in this particular class, we will be learning specially our focus will be on the definition, the degree of polymerization, the functionality of monomers and their significance. So what is a polymer? That means how will you define a polymer? So the word polymer is derived from two Greek words, which is poly, which means many, and mers, which means parts or units. So a polymer is a large molecule which is formed by the combination of many small molecules. So the individual small molecules, which is known as the monomer, that is from which the polymer is formed, this is known as the monomers. And the process by which the monomer molecule or the small molecules, they get linked to form a big molecule is known as the polymerization. So this is a small illustration of the what do you mean by monomer, what do you mean by polymer, and what do you mean by polymerization. So here in this we can see that the monomer unit is a CH2 double bond CH2, and this is a ethylene molecule. So when n number of ethylene molecules, they get added up via process of polymerization, we get a large molecule which is a polymer. Now in the difference between this monomer and the polymer is that you have got a double bond here, and whereas in this there is a single bond here and n number is added to this to form a polymer. So more illustrations are shown in this slide. Here you see that the highlighted region is the monomeric unit, and in this case it is a ethylene molecule, that means the CH2, and more number of ethylene molecules they have added up to form a single molecule which is a polyethylene molecule. Now in the case of the second example, the highlighted region is a monomer belonging to vinyl chloride. So that means CH2CHCl, this is the vinyl chloride, and again more number of vinyl chloride molecules have added up to form a single molecule which is known as the PVC or the polyvinyl chloride. Now in the third example, we have got the propylene molecule as the monomeric unit, that means the CH2CHCH3, and more number of such units have added to form a PP, that is a polypropylene molecule. So we have got two groups here. One is the straight chain carbon, which is the backbone chain, and the side groups that are attached to the carbon chain. So the side chains or the side groups that are attached to the main carbon backbone chain, that gives special properties to the polymer molecules, and that we will be discussing in the coming slides. So we come to a second terminology, which is the degree of polymerization, which is known as the DP. The number of repeating units or the number of monomeric units that are attached in a polymer chain, that is called as the DP, and DP is equal to Mn divided by M. Whereas the capital M stands for the molecular weight of the polymer, whereas the small m stands for the molecular weight of the monomer. Now let us take the example of a PVC molecule. Here the monomeric unit is CH2CHCl and its molecular weight is 62.496 grams per mole, whereas the molecular weight of the PVC molecule is 21,150. So what is the dP of the PVC? It is 21,150 divided by 62.496, which we have used this formula, and it comes out to be 338.42. Now, how is the number of monomeric units, or the dP, or the polymer chain length, how it affects the properties of a polymer? That is what we are going to learn in these slides. So the properties of a polymer, that means the elastic modulus, the strength, or the physical properties, or the chemical properties, all these are affected by the polymer chain length. For example, the melting temperature of the polymer increases as we increase its molecular weight. So at room temperature, that means polymers having very short chains, that means roughly 100 grams per mole, they exist as liquids. Now when we increase the monomeric units, or when we increase its molecular weight by 1000 grams per moles, the polymers, they change their physical properties to waxy solids and soft resins. Now, if we further increase the molecular weight of polymers to around approximately 10,000 or several million grams per mole, the polymers, they exist exclusively in the solid state. So this slide is again another example of further illustrations of how the dP, or how the number of monomeric units, or how the polymer chain length affects the properties of a polymer. So let us take the simple molecule, that is a ethane, that is CH3CH3. It is a gas molecule at a room temperature. Now we increase the chain length to double. That means we are getting a butane molecule, and this is a liquid fuel. Now in the butane molecule, we know that because of its large size, the mobility is restricted as compared to a ethane molecule. Now, when we increase the chain length to a 6-fold, for example, in paraffin, now this is the molecular formula of paraffin, we get a waxy substance. In this case, the solid-like property of paraffin is a reflection of the entanglement of its long molecules when they move. That means, in short, I can say that the movement is getting restricted. Now, we increase the number of repeating carbon units to say 2000. So that means here we have got 2000 of CH2CH2 ethane molecules, and we have got a polyethylene polymer now. Now this is a strong brittle solid. Here in this case, the polymer molecules have become so long and entangled that the movement is completely restricted. Now another terminology which we will come frequently across while studying polymers is the functionality. So we know that monomers are repeating small units in a polymer. So can all molecules behave as a monomer? No. So what are the criteria that has to be followed for a monomer, for a molecule or an organic molecule to become to behave as a monomer? So here comes the concept of functionality. So how will you define functionality? It is the number of bonding or reactive sites in a monomer. The reactive sites or the binding sites can be a double bond, a triple bond, or the presence of functional groups like a NH2OH, COH, or a SH, or any number of functional groups. So that means for an organic molecule to behave as a monomer, minimum 2 functional groups must be present. Now let us see the illustration of acetic acid. Now what is the formula of acetic acid? It is CH3COOH. So we have got only one functional group, that is COOH. In benzoic acid, again there is only one functional group, that is COOH. In ethyl alcohol, that is C2H5OH, we have got one functional group, that is OH. In aniline, again we have got one functional group. Here methyl isocyanate also has only one functional group. So all these examples of molecules are cannot behave as a monomer because of the presence of only one functional group. Now let us take the example of a vinyl monomer. Here you see this is a vinyl halide. Vinyl stands for CH2 double bond CH, and X stands for the halogen. Now because of the presence of a double bond, this vinyl halide will behave as a monomer. Why? Because this double bond will break to give rise to 2 edge single bonds. So that means this single bonds, they are single valencies, they are free valencies from via which the more number of monomeric units can attach. So that means this vinyl halide is an example of a monomer. So these are different illustrations of the monomers in which the double bond is there. So that means the presence of a double bond ensures that the organic molecule will behave as a monomer. So in this case, you see that this is a C double bond C, and the side groups attached are CH3, the chloride or the fluoride, or simply a H. So that means all these, that means the propylene molecule or the vinyl chloride or the tetrafluoroethylene, all these will behave as monomers. So the double bond is the vital feature that allows these monomers to form a long polymeric chain. The highlighted areas, that means here this is CH3, the chlorine or the fluorine, they are the side groups on these monomer molecules, and these side groups, they give specific properties to a polymer molecule. Now in the previous slides, I have shown you molecules where a double bond is present, and this double bond is an essential criteria for a molecule to behave as a monomer. But besides a double bond, a triple bond can also ensure whether the molecule will behave as a monomer or not. That means the triple bond is also an important criteria whose presence will ensure that the molecule will behave as a monomer. Now in these examples, we are seeing that in all these examples, the molecule does not have a double bond or a triple bond, but still they are behaving as monomers. So what is so special about these molecules? So in the first example, we are seeing that there are 4 carbon atoms, and at the edge of which are 2 functional groups, that is COH. 2 COH groups are attached. So this will behave as this molecule, which is the name is 1, 2, 3, 4. That means it is 1,4-dihexanoic acid, and this will behave as a monomer. In the second example, the benzene ring has got 2 COH group at the para position, and this molecule will again behave as a monomer. In the third example, 2 NH2 groups are attached at the end of the 1, 2, 3, 4, 5, 6. That means at the edge of the 2 carbon atoms in this molecule. Here this behave as a monomer. In the case of ethylene glycol, we are finding the presence of 2 OH groups. So all these are examples of monomers. In the above examples, the functional groups are highlighted in yellow. Each molecule has got 2 functional groups. So what is the significance of functionality in polymers? When the functionality of monomer is 2, linear or straight chain polymer molecule is formed. Examples are vinyl monomers, adipic acid, ethylene glycol, amino acids, hexamethylene diamine, etc. But when the functionality is 3, a 3-dimensional network polymer is formed. Example is the phenol, melamine, etc. When a trifunctional monomer is mixed with a bifunctional monomer, a branch chain polymer is formed. And when a bifunctional monomer is mixed with a trifunctional monomer, a 3-dimensional network polymer is formed. So in short, I can say that the functionality is in fact determining the properties of the polymers in various respects, and which we'll be learning in the coming lectures. So thank you for listening to me, and hope you have enjoyed this video. If you have any comments or any doubts, we will be solving your doubts in the doubt clearing session. Thank you.